Welcome back, Chemistry 30. So this is the last video here. So we looked at, so this is MS1.3, covalent bonding. We just looked at this resonance structure. It has a double bond. One thing to mention about single, double, triple bonds, etc. Think of it like this. Think of an element bonded by a single bond versus double bond versus triple bond. Now I tried to draw this to illustrate that the atoms become closer together as the number of bonds increases. So elements are closer together as number of bonds increases. And kind of the reasoning for that is if you have more electrons. So here you'd have 2 electrons, 4 electrons, 6 electrons. You can think about it as more electron, quote-unquote, glue as electron number increases. So it causes them to be pulled together and held more securely, more attraction, the more electrons you have. So you can think of it as more electrons mean more electron glue, and the bonds become smaller as you increase from single to double to triple. So single to double to triple. That's one thing that I wanted to mention there as we go from one to the other. All right, let's look at the last example here. So the last example deals with an ion. And Lewis structures for ions, they can also be made for polyatomic ions. The methods are the same, except that charge must be taken into account. If it's a negative polyatomic ion, then we add an electron. And if it's a positive ion, it needs to be subtracted. So we'll look at the case of the nitrite ion, NO2 negative. So we have 1 N plus 2 oxygens plus 1 extra electron. So you can take a look. We have that extra electron there, which must be accounted for. So we just simply treat that as add 1 more electron. Now, if you look at the group numbers for each of these, nitrogen is in group 5, so it has 5 valence electrons. And oxygen, of course, we know that one by now. It's group 6, so we have 6 valence electrons. But then we have this extra one right here on the end. So here we have 5, and you can see why we need that extra one, because we end up with an odd number here, right? So we have to have 1 extra one added to make it an even number. So 17, 18 valence electrons we have. Okay, so I put this together. So nitrogen will be in the middle. Oxygen, now I can just put them on opposite sides. So 2, 4, I've used up 4 electrons. Obviously I need to have more. All right. And so 2, 4, 6, 8, 10, 12, 14, 16. And of course I have 1 pair left over, so that's going to go there. All right. So I have that. And it's like a case that we've looked at before. It's like the SO2 example up above. 2, 4, 6, 8, 10, 12, 14, 16, 18. That oxygen's good with 8. That oxygen's good with 8. And that nitrogen has 2, 4, 6 only. 2, 4, 6. So yes, it's a case that either that one's going to move or the other one. So we have 2 structures for this. One I forgot to mention, since it's a polyatomic ion, just like before, to illustrate that, we show it like this, square brackets with the overall charge out there. So we could have it look like this. So that set moved down to make a shared pair there. Okay, and then we look at here, 2, 4, 6, 8, 10, 12, 14, 16, 18. This oxygen still has 2, 4, 6, 8. That oxygen still has 2, 4, 6, 8. And the nitrogen 2, 4, 6, 8. We're good. So I could have done that, or of course I could have had the other oxygen contribute. So this one would have stayed like this. And the double bond would have been here. So it doesn't really matter there. I could have done either one. All right, so that's it. You should be able to do the assignment now, and we'll see you again.